Welcome to a screencast on enthalpies of formation and reaction enthalpies. The objectives of this screencast are to state the meaning of delta H of formation, to write formation-reaction equations, and to use tabulated delta H of formation values to determine the delta H for a reaction and vice versa. Let's start by looking at a few reaction equations, thermochemical equations, and the first one is nitrogen and hydrogen reacting to make hydrazine N2H4 with an associated delta H value. Okay, here's another one. Iron reacting with oxygen to make iron 3 oxide Fe2O3 with its associated delta H for this reaction. And one more. Carbon and hydrogen and oxygen all reacting together to make C6H12O6 or glucose with an associated delta H value for this reaction as well. Now, a couple things to note about all three of these reactions. In every case, we are starting with elements in their standard states and forming a compound. And in fact, in each case, we're forming 1 mole of a compound. So all of the reactions above have a compound being formed from the elements that make it up, its constituent elements, in their standard states. Now, for this type of reaction, there's an associated delta H, and we call the delta H that's associated with this type of reaction a standard enthalpy of formation. We symbolize it by delta H sub F, where the F is for formation, and then the superscript 0 is for standard or under standard states. And it's called a standard enthalpy of formation because we are forming 1 mole of the compound from its constituent elements in their standard states. And this is something that chemists universally use. It's our standard. Now, it turns out these are really useful values. Standard enthalpy of formation, delta H sub F values are very useful. We'll see in just a minute. And because they're so useful, they are found in tables, in chemistry textbooks, in reference books, and these are just a few examples of some standard enthalpies of formation at 25 degrees Celsius. So carbon dioxide, CO2 gas, has a standard enthalpy of formation, a delta H sub F, of negative 393.5 kilojoules per mole. So starting with carbon and oxygen in their standard states, when a mole of carbon dioxide gas is formed, there's a delta H value for that reaction of negative 393.5 kilojoules. Now, same idea for iron 3 oxide, forming 1 mole of that from its constituent elements, has a delta H of negative 824.2 for that reaction equation. Water, its delta H of formation is given, hydrazine, similar idea, and zinc 2 sulfate or zinc sulfate has a delta H of formation of negative 982.8 kilojoules to form 1 mole of that substance from the constituent elements zinc and sulfur and oxygen. Okay, now how is this useful? How do we use delta H of formation values? Well, it turns out, and this can be shown using Hess's Law. It's a consequence of Hess's Law and enthalpy being a state function. It turns out for any chemical reaction, the following relationship is true. The delta H of reaction can be calculated using this equation where sigma stands for sum, n stands for the stoichiometric coefficient of a given substance, and delta H of formation is, of course, an enthalpy of formation value. So the delta H of reaction for any chemical reaction is the sum of the delta H of formations of the products of the reaction, each multiplied by its stoichiometric coefficient, and then minus the sum of the delta H of formation of the reactants for this reaction, multiplied each of them by their stoichiometric coefficient. And this is pretty easy to see via an example, so let's use enthalpies of formation to calculate the delta H of reaction for the combustion of propane. Propane reacts with oxygen to make CO2 and H2O. Okay, how do we do this? Well, first of all, we go to the table and we look up the delta H of formation values. Delta H of formation for propane is negative 103.8 kilojoules to form 1 mole of that. Oxygen, O2, is actually already in its standard state, so it takes no extra energy to form that. It's already formed, so to speak. So the delta H of formation of O2 gas is 0. And in fact, any element in its standard state will have a delta H of formation of 0 because it's already in its standard state. CO2 has a delta H of formation of negative 393.5 kilojoules to form 1 mole of that, and H2O liquid, negative 285.8 kilojoules per mole. Okay, so now to get the delta H for the reaction, we're going to sum up the products. So product is CO2. It has a negative 393.5 kilojoule per mole enthalpy of formation. We multiply that by its stoichiometric coefficient of 3 moles. And then we add that to the next product, the other product, H2O, which has a delta H of formation of negative 285.8, multiplied by its stoichiometric coefficient of 4 moles. And then we subtract the total of our reactants, propane, negative 103.2 kilojoules times the coefficient of 1. And then oxygen, if it wasn't 0, we'd be multiplying it by 5. Since it is 0, it doesn't really matter, but we're going to multiply whatever the delta H of formation of this substance is times its coefficient of 5 in this case. And when we do that, we get negative 2,220.2 kilojoules for the delta H for this reaction. So it's pretty straightforward. You look up delta H of formation values, use the formula, use the stoichiometric coefficients, pay attention to doing the math right and significant figures and units, and it's pretty much plug and chug. Now, it's worth noting we could, of course, also go the other way. So, for example, if we knew that the delta H for this reaction was negative 2,220.2 kilojoules, we knew that was the heat of combustion of propane, and let's say we knew the delta H of formation of CO2 and H2O, but we didn't know the delta H of formation of propane, this would be kind of like we know the answer and then some of the parts that add up to the answer, and we could solve for a missing delta H of formation. So we can get a delta H of formation from a delta H of reaction and some other delta H's of formation as well. So that's the vice versa part. And that is actually it for the enthalpies of formation and reaction enthalpies screencast.